This talk is about optimal coding for randomized Kolmogorov complexity and its applications. Let's begin with the following question. How much information is contained in some string X? One answer from information theory is the following. So first, we assume that this X is selected according to some distribution D. Then the information content of X is defined as this value, minus logarithm of the probability that X is sampled from this distribution D. And this is the optimal encoding length in expectation over X given the description of this distribution D. Another answer from algorithmic information theory is the following. We measure the information of X by Kolmogorov complexity of X. This is defined as a, roughly speaking, minimum program size that outputs X when it is given to some fixed universal Turing machine. Particularly, this notion of information content is a quantity that only depends on the underlying distribution. But in algorithmic information, we can measure the information of string X for each individual string, and it matches our intuition for information. For instance, the Kolmogorov complexity of n zeros is approximately at most log n, and the Kolmogorov complexity of n random bits is with high probability approximately n. And the information of ith prime is at most the information about I plus information about the definition of prime. Now we have two definitions about information. Then it is natural to ask their relationships. Particularly, does the algorithmic information coincide with the information content for X sampled from some distribution D? The answer is yes, on average, for every natural distribution. On one hand, for every distribution D, the Kolmogorov complexity is at least the information content with high probability. The other direction is often called optimal coding theorem. For instance, for every distribution whose mass function is time-unboundedly computable, the Kolmogorov complexity is approximately at the most the information content, ignoring some additive tab for all strings in this plot. So under such distributions, the algorithmic information coincides with the information content on average. In this work, we consider the time-bounded variant of algorithmic information. We can obtain a string X from K of X bits, but its reconstruction may require exponential time. So in the time-bounded world, it may require more bits to obtain the string X. And to capture the algorithmic information in time-bounded setting, we can discuss about time-bounded Kolmogorov complexity. In the time-bounded Kolmogorov complexity, we add an additional parameter, t, and we execute the universal Turing machine only in t steps. The conditional Kolmogorov complexity of X given Y is defined as in the almost the same way, but we can use the additional advice string Y. This can be regarded as an algorithmic information of X that is not contained in the conditional string Y. And in this talk, we also use the notation K poly. And when we consider time-bounded settings, additional computational resources can be helpful to generate X, particularly randomness. And there are two basic definitions, randomized Kolmogorov complexity and probabilistic Kolmogorov complexity. The main difference between these two notions is the order of randomness and program. In randomized Kolmogorov complexity, first we find a program, and this program is given randomness, and with high probability, this outputs X. In probabilistic Kolmogorov complexity, first we select randomness, and depending on this random string, we find the program that outputs X with high probability over the choice of randomness. So the program can depend on the randomness. And this is the formal definition of randomized Kolmogorov complexity. And this is a definition of probabilistic Kolmogorov complexity, where we switch the order We can also define the conditional versions in the same manner as the standard Kolmogorov time-bounded Kolmogorov complexity. And by definition, we have these inequalities. And these are lower bounded by the time-unbounded Kolmogorov complexity. And in terms of algorithmic information, the randomized Kolmogorov complexity is more natural than the probabilistic Kolmogorov complexity, particularly to send a string X. In the setting of randomized Kolmogorov complexity, one person only needs to send the minimum program, and it takes RK of X bits. Then the other party can select randomness, and by executing this program, it can obtain the string X. But in probabilistic Kolmogorov complexity, since the program can depend on the randomness, the sender first needs to select randomness. And depending on this randomness, the sender finds the program and it sends the program. And in addition to this program, this sender also needs to send the randomness. Then the receiver can obtain string X by executing the program. Then the total amount of bits to send X is the value of probabilistic Kolmogorov complexity plus the amount of randomness. And this can be much larger than the string X itself in general. One interpretation of probabilistic Kolmogorov complexity is like as algorithmic information in the parallel world where public randomness is available or some randomness is shared beforehand. But in general, this is not the case in our world. And under the well-believed derandomization assumption, these values, pk and rk and k, is approximately the same. Although this is seemingly out of reach at present, but establishing some property in probabilistic Kolmogorov complexity is sufficient to have a certain belief that the same property also holds for rk and k. And in this work, we consider the coding theorem for these time-bounded algorithmic information notions. From the inequalities between them, we have these implications. And it is known that for every p-computable distribution, this is a distribution whose cumulative distribution function is polynomial time computable, admit the coding for deterministic Kolmogorov complexity. But we can consider conceptually broader and natural class of distributions called p-sampleable distribution. This is a distribution sampled by polynomial time probabilistic Turing machine. And it is open whether the p-sampleable distribution admits the coding for deterministic Kolmogorov complexity. And it is the same for RK. Fortunately, we have coding theorem for pk poly for every p-sampleable distribution. But again, the pk is a bit unnatural notion for algorithmic information with randomness. And in this work, we asked a class that admits the coding theorem for RK poly. And as a result, we first find the class next bit PPP predictable distributions. And we show that this class admits average case optimal coding for RK poly. And in worst case, we obtain almost optimal coding for RK poly. And then we use this coding theorem to resolve some open questions in meta-complexity community coming from the lack of coding theorem for RK poly. First, I formally define the notion of next bit predictable distributions. So we say that a distribution D is next bit predictable if for every polynomial there exists some probabilistic polynomial time algorithm M such that this holds. For every string in the support, and for every position I, and for every bit, this algorithm is given a prefix string of X up to I-1 and the next bit B, and approximate the next bit probability within some additive tab and with high probability. Oh, sorry, this is 1 minus 1 over P. And for convenience, we also define the notion next bit predictable on average. This means that this orange part holds on average over the choice of X according to distribution D. Then our coding theorem for RK poly is the following. If the distribution is next bit predictable on average, then we can obtain average case optimal coding for RK poly over the choice of X according to distribution D with high probability the RK is bounded by the information content. And for smaller error probability, we need to pick larger time bound. In addition, if the distribution is next bit predictable in worst case sense, then we can obtain the worst case almost optimal coding. And the term almost optimal comes from this additional small constant epsilon. Actually, the proof of this theorem is very elemental, in my opinion. The proof idea is based on the arithmetic coding, where roughly speaking, we encode each string X by using the approximated value of this quantity, the value of CDF of lexicographically previous string, and the value of probability. And these values can be approximated by using the next bit predictor. But since the next bit predictor is randomized algorithm, the approximated value can vary according to the randomness. And in the setting of RK, we cannot share the randomness in encoding step and the decoding step. And the variety of the error in approximation can cause the failure of decoding. To manage this point, we use a technique of adding noise and rounding. This was also used in the previous work in a similar context. Namely, we first add some small noise to approximated values, then we round it to some grids. And we need to share the amount of noise in both encoding and decoding steps. But the description size is very small, logarithmic, so we can contain the amount of noise as an additional log n factor. And this idea is sufficient to show the case of average case optimal coding. For worst case almost optimal coding, we need to consider a bit more, but I skipped the detail here. And let's move on to the applications. Actually, our coding theorems is proven elementary, but interestingly, it is sufficient to resolve some open problems recently posed in the meta-complexity community. And in this talk, I focus on the first one. Actually, this is our original motivation to study optimal coding for RK poly. The symmetry of information is a very basic natural property about information. Let's say we have two information sources, and the symmetry of information says that the information about Y that X has is equal to the information about X that Y has. And in the standard information theory, it is expressed by using mutual information. Proving this equality is very fundamental. Actually, it follows almost by definition of conditional probability. Interestingly, the analog also holds in algorithmic information. This is proved by Kolmogorov and Levin, and this is much more non-trivial statement. Then, what happens if we consider time-bounded setting? In fact, this question has been paid attention to as a test case to show some situation where we essentially need exhaustive search, even before formulating P versus NP problem. After that, some follow-up work noticed that the notion of time-bounded symmetry of information has something to do with the very fundamental cryptographic primitive called one-way function. Roughly speaking, one-way function is a function whose computation is easy, but inverting its average case hard by default against polynomial time adversaries. And Longbray and Watanabe proved that if we have such a one-way function, then the time-bounded symmetry of information does not hold. Then they posed the question whether some asymmetry of time-bounded algorithmic information characterize one-way function. In stock last year, we gave the first affirmative answer for their question based on the average case variant of symmetry of information for PK poly. And the statement of average case symmetry of information is this. We consider any sampleable distribution over pairs of strings. And when we select a pair according to this distribution, the symmetry holds for PK poly with high probability. And we proved that a one-way function does not exist if and only if average case symmetry of information for PK poly holds. But again, in terms of algorithmic information, the notion of randomized Kolmogorov complexity is seemingly more natural than PK poly. So we can ask the same question for RK poly. And the question is whether this average case symmetry of information for RK poly characterizes the existence of one-way function. Unfortunately, the previous work failed to prove this, but instead they proved the characterization for quasi-polynomial regime, where we consider one-way function which is secure against quasi-polynomial time adversaries, and we also consider average case symmetry of information for RK quasi-poly. The proof is based on not optimal coding theorem based on the non-existence of one-way function, and due to this non-optimality of coding theorem, we could not apply the same technique for polynomial regime. And in this work, based on our coding theorem, we resolve this open question. So we can characterize the existence of one-way function based on average case symmetry of information for RK poly. Namely, we can characterize asymmetry of computation based on average case asymmetry of very natural randomized algorithmic information. I will briefly present the proof sketch. Particularly, the core part is the following implication. If there is no one-way function, then average case symmetry of information holds for pairs selected according to some sampleable distribution. For convenience, we represent each part, the first part and the second part, by using these notations. And in the case of PK poly, we have the coding term for every sampleable distributions. Now, since the pair of x and y is sampled according to the sampleable distribution, the value of PK poly of x and y is equal to the information content on average. And additionally, we use the previous work by Impagliazzo-Ruby and Impagliazzo-Levin, and we can show that under the non-existence of one-way function, we can make the conditional distribution of the first element given the second element, and the conditional distribution of the second element given the first element sampleable. Then we can also use the coding theorem for these conditional distributions, and we obtain conditional coding. Namely, these quantities in algorithmic information coincide with the world of statistics. And in this world, the statement of symmetry is trivial. And since on average, these quantities match to the amount of probabilistic Kolmogorov complexity, we obtain the same statement for PK poly. And now let's consider the case of RK poly. In this case, we do not have unconditional coding for sampleable distributions, but instead we have the coding for next bits predictable on average distributions. But it is unclear whether this is sufficient to connect the world of RK with the world of statistics. But now we can again use the assumption of the non-existence of one-way function. Actually, based on the same previous work, under the non-existence of one-way function, we can also show that every sampleable distribution is actually next bits predictable on average. Now we can apply the same strategy as in the case of PK, and we obtain, on average, the symmetry for RK poly. To sum up, in this work, we considered optimal coding theorem for RK poly. Based on this coding, we resolved some open questions in meta complexity community, particularly for RK poly. Okay, that's all. Thank you for your attention.